going to be talking about is increasing your electric metering accuracy and how a utility can increase their bottom line. As I said before, my name is Steve Lindsay, Marketing and Sales Manager. We're in Pine Tops, North Carolina, by increasing their metering accuracy. So what we'll talk about today is we'll cover the IEEE standards for metering accuracy. Then we'll determine where utilities are losing money. Then we'll talk about how you can calculate what your utility could save by switching to high accuracy extended range current transformers. And then we'll cover the different applications where these high accuracy current transformers are being used and how you can implement them on your distribution grid. Okay, first, the IEEE has very, very distinct definitions for metering accuracy. And so let's kind of go over those right now. If we start from the bottom going to the top, which will be the least accurate going to the most accurate, there is an accuracy class of 1.2, and there's also an accuracy class of 0.6. Those are both indicating instruments. What that 1.2 and 0.6 means is that any current transformer in that class has to record current accurately between 1.2% below or 1.2% above what we call nominal current. So if you have a current transformer that's rated a 200:5 ratio, that would have to fall within, in this case at the bottom, 1.2% below or 1.2% above 200 amps. The one that most utilities are familiar with is what we call revenue class metering accuracy, or 0.3%. So in terms of percentages, your current accuracy would have to be measured between 99.7% and 100.3%, all along the scale of the current transformer. Because there's been some significant increases in technology with different metals being used for current transformers, there's also been developed a 0.15 and a 0.15 S class. The 0.5 is what we call high accuracy, and then we have a special high accuracy. And we'll go in depth into what those mean now. So if we kind of take a look at a chart of where a current transformer would need to be in the 0.6% class, you have to be anywhere between 0.6% above or below what we call nominal current. And this also runs the gamut from 100% of your nominal current all the way through what we call the rating factor. So you can have a rating factor up to 4 in a current transformer. So for instance, if you had a 200:5 rated CT, that could go up to 800 amps and would still have to measure accurately. Anything below nominal current, or in this case below 200 amps, the accuracy is allowed to fall off by double at that point. Okay, we get to revenue class accuracy, you can see that the bandwidth kind of starts to narrow a little bit, where from 100% of nominal current through your rating factor, you go down to 0.3%. But as you get into lower load applications, as your current decreases, the accuracy falls off in a current transformer. Our 0.15 class, again, narrows that bandwidth down. Anything above your nominal current will be at 0.15%. So your CTs will be more accurate, therefore your meter will be more accurate. But again, as you fall down below your nominal current, as you start getting to low loads, your accuracy is allowed to fall off again by double to 0.3%. Still much more accurate than the revenue class, but not the most accurate that's out there. The 0.15 S class is the most highly accurate recognized class within the IEEE. And that basically goes from 5% of your nominal current through the rating factor, all at 0.15%. So we've significantly narrowed down the band of inaccuracy that gets eliminated, and we've kind of extended the range a little bit as well. Now, ABB also makes instrument transformers at the medium voltage level, which can go beyond the 0.15 S class. Not any more accurate, but we've increased the range for that, all the way down to 1% of your nominal current. So again, if we go back to that example of a 200:5 rated CT, it would measure any amps from 200 through a rating factor of 1.5 in this case to 300 amps, all at 0.15% accuracy. So you have a very, very highly accurate current transformer all along the whole current or the whole load feeding into your meter in order to get more accurate readings. Okay? So those are the different accuracy classes as defined by the IEEE. And then one where we actually exceed in a lot of our applications. So let's talk a little bit about the true accuracy of a current transformer. What we did, we're actually releasing a new product here this week at Automation and Power World. So we said, well, let's take a look at some of the data of how our current transformers actually test. We test every current transformer that leaves our factory. And so we said, let's take a 10,000 unit sampling of all the data and see where the accuracy truly stands. If we look at what we said before in the 0.3% accuracy class, you can go down to 10%. So we test everything at 10%, has to be at least 0.6% accurate. So we found that the median accuracy of those CTs fell at about 0.45. Okay, so there was quite a bit of inaccuracy as the load went lower. We also test them at 100% of nominal current. So in that case of a 205 CT, we'll test them at 200 amps. You can see that the median right there is about a 0.25% accuracy. Okay, just barely inside the range of 0.3%. Okay, still pretty accurate, but you can see it's still at kind of near the top of where the 0.3% accuracy is. And then we tested our high accuracy CTs for test data, and you can see that the median falls at 0.05 and below, so they become much more accurate. Okay, so what this does for the utility is it helps become much more accurate. You'll get more revenue based on no losses in here, and the customer will get a true billing payment as well every single month. Let's talk about where utilities lose their money when it comes to this accuracy range here. Anytime a current transformer is feeding data into a meter outside of this range here, utilities really start to lose money. Right? It's not as accurate as what it can be. When you have a more highly accurate CT, that's when the utility starts to actually save money. The meter will actually register more accurately for the utility. The utility can save, it might be a very small percentage. You say, okay, well, if we go from 0.25 to 0.05, that's a small fraction. Well, when you're dealing with some of the larger applications and larger utilities which have a lot of metering on their units, this can add to a very significant amount of money on a monthly basis. Let's talk about the different applications where we would find these highly accurate CTs. We're releasing a new product this week at Automation and Power World called the AccuRange current transformers. We have 3 different types that are coming in. These are the vast majority of current transformers that a utility would use at the secondary revenue metering. Again, this will increase revenue metering, and one of the other benefits to these also is that you can decrease the amount of stock that you have, because these 3 CTs right here, these specific ratios, will pretty much be anything that a utility would use in the course of any kind of secondary revenue metering. This particular unit, called the CBTS, these are very commonly found in what we call a trans socket. This is what you'll find on the side of a gym or a McDonald's or a CVS type of application or type of installation. And then you would typically have a meter box right next to it where the data would be fed into the meter. You can see these are bar type. You can actually kind of see right here the bars on either side of the current transformer inside the trans socket. The primary would be loaded into that and coming back out and then flowing into the store or whatever other installation there is. We also have one that's very commonly found in pad-mounted distribution transformers. Okay, this is called the CMVS. Okay, you would see these outside of slightly larger installations, a green box and typically a meter on this side of that. And so, we have ones that are specifically designed just for that. One of the other nice things about these here is that they are able to withstand higher heat because what will happen, especially in the summertime, especially in the south or in high temperature climates, the temperature inside there will become very hot. CTs typically will derate for accuracy once the temperature becomes very high. These are specially designed to withstand temperatures up to 85 degrees C inside that pad-mounted distribution transformer. We also have what's called the CMFS. Typically you'll see these either up near a distribution transformer or when the distribution transformer is going directly into an installation. You'll see these hanging on the wires in an outdoor environment and then connected to a meter as the electricity goes into a building. If you drive around lots of cities, you'll see these if you just kind of take a look up. So let's talk about the savings that you can find at the secondary metering level. The secondary metering point would be something like we talked about before. It could be a gym, it could be a small industrial complex, maybe a small welding and manufacturing facility, a McDonald's, a Chili's, a CVS, something that's going to have a 480 volt service coming into it. Okay, so typically we'll see something in the range of maybe $48,000 a year, $4,000 a month. Okay. One of the things that we're going to take a look at that's important, if you remember from the accuracy classes, as you fall down below nominal current, we said that the accuracy range was allowed to double around that on the IEEE standards. So the percent of time that you're above what we call nominal current, or will that be a high use time? And the time that you're below nominal current or a low load would be something similar. So for this example, we'll say 50% of the time we're above nominal current, 50% of the time we're below nominal current. So we'll just take an industrial application as an example. Maybe a small welding shop and fabrication shop. Guys are working there maybe 10 hours a day, maybe 12 hours a day on a busy day if there's a lot going on. But the rest of the night, when they go home, you might have some security cameras on or some security lights, outdoor lights, maybe a fax machine that's still on. Maybe some people leave their computers on. So you have a very, very low load compared to what's going on during the day. Okay, so we'll have a low load period, and we'll have a normal or high load period. That's going to be very, very important as we look at the different calculations. So if we took the annual usage times the percentage of time above nominal current, and you multiply that out times 0.0015. Now where does the 0.0015 come from? Well, that's the difference between 0.03 and 0.015% accuracy. So that'd be the differential between those two. So if you multiply that out at times of above nominal current, you can save $36 a year. If we take a look at annual usage times the period of time below nominal current times 0.0045. Again, that's the difference between 0.6% and 0.15%. Okay? You could save $108. So potential savings for a utility on an installation like this with say about a $48,000 a year electric bill could be $148. You say, well, that's not a whole lot. Okay? Why would I really kind of change anything that I'm doing now for $148? Well, the difference in price from a regular CT to a highly accurate CT is about $25. You see that would pay for itself in about 2 months' time. You say, well, I'll save $125. A typical, utility could have anywhere from several hundred of these to into the thousands if you look at large investor-owned utilities. So you take that savings and multiply that out. It's a very, very significant savings for a utility, and that's savings for just 1 year. These are typically 20 or 25-year products, so you're really going to extend that over a 25-year period of time. Okay. Secondary revenue metering, that's the most common application. There's more of those than anything else. But we also have primary metering applications as well. We'll start to see some more significant savings here. Primary metering would be used at, I'll just use my factory as an example in Pinetops, North Carolina. Okay. We have 15 kV circuits. We meter right off of the primary electricity there. So we're doing it at much higher levels here. Typically, you'll see these in rack-mounted units outside as electricity comes in directly from the feeder into the installation. Meter would be down below, usually at eye level. And so you have those typically mounted in racks like that. We also have them in combination units. The current and voltage both can be in one installation as well. Basically, that helps for ease of installation for the lineman. Let's take a look at the savings at the primary metering level. Annual usage. I'm taking, again, my factory as an example. We pay about $1 million a year in electricity. Percent of time above nominal current. Okay, and kind of how I came up with that is my factory as this example. First shift, 7 o'clock to 3:30. We're going full bore. Everybody's working. Every station's manned. We have annealing furnaces which are going full time. Everything in the factory is going. Computers, fax machines, lights, you name it. We're going all out on first shift. Second shift. We run typically over half of what we do on first shift. We still have all the annealing ovens going, so that's a big consumer of electricity. But by second shift, a lot of the office staff have gone, except for the marketing guys, of course. We're always there late. So that kind of drops off. We don't run all products on second shift, but we do some. So I said, well, let's take a 67% time that we're above nominal current. I said, well, third shift, we're still using some electricity, but it's not full bore. About the only things that we're running are 1 or 2 product lines, our annealing ovens. And so we do use some electricity, but it definitely falls down below normal usage at that point. So doing the same calculation that we did at the secondary level, if we say A times B, or $1 million times 2/3, times the difference between 0.3 and 0.15, there saves about $1,000. And then we see even more significant savings when we go down to very, very low loads, okay? $1,500 almost for savings. Savings of almost $2,500 over 1 year. These CTs would cost about maybe $100 more than a regular CT. Okay? To save $2,500, you spend $100. That's a pretty good payback. Okay? Very few utilities, very few people would say, I don't want to spend $100 to save $2,500 in 1 year. So it's a very, very quick payback. Over the life of the units, 20 or 25 years, very, very significant savings. Where else do we see applications that we can use high accuracy current transformers as well? One of the most classic examples is any kind of renewable energy. Wind farms, solar panels and solar farms are very, very heavily dependent upon wide range, high accuracy CTs. Why is that? Well, some days the wind's blowing at 25 or 30 miles an hour, but sometimes you have a light breeze. Okay? The people who build wind farms spend a lot of money. They want to be able to get their money out of it. And the only way they can recoup their investment is to actually have those turbines spinning, generating electricity, and having the utility purchase that. Okay? So they want to get as much billing, okay, that they possibly can. That's how they recoup their investment. So we have very, very specific current transformers are designed for applications like that as well. It's a great use of that wide range that we talked about, from 1% of nominal current all the way to the highest rating. Substation retrofits is another big one. Okay? Oftentimes, a power transformer like you see here will have put, say, a relay protection class CT inside when it was first built, but maybe the utility later on wants to add some metering at the substation. These are easily installed over the bushings, and you can not purchase a high voltage instrument transformer, but rather one of these here, and get pretty much the same accuracy that you will with a high voltage instrument transformer for a whole lot less money. Annual usage that might pass through a 138 kV substation, about $120 million a year. That'd be a tie point usually between transmission going down to distribution. So a municipal, a co-op, or even an investor-owned utility would buy power from a transmission or a generation company, and maybe they want to add second metering check just to make sure they're paying the right bill, as it would be a good example. Time above nominal current. Okay, you spend the money, tens of millions of dollars on a 138 kV substation. Generally, that's going to be above nominal current all the time. So percent below nominal then would be 100 minus 0. Obviously would be 0. But if we do the math there, okay, we can see the savings would be very, very significant. Okay, up to $180,000 a year. The difference between 0.3% of revenue grade metering and then high accuracy metering. Most of these though already have high accuracy metering, so this wouldn't be something the utility would typically say, I need to add this, okay, I need to change this. Usually it's already metered at that level with high voltage instrument transformers, but I just wanted to show, as you scale up the amount of electricity that you use, you can really start to save a whole lot more money, and that's really where your cost driver is going to be. So even if we looked at secondary revenue metering, where you typically have a very small electric bill, not according to our houses, but for a business it's relatively small, do primary metering, where you have some more heavy industrial type uses, okay, savings can be very small, but spread out over an incredible number of installations, or a few smaller commercial and industrial applications where you get the primary metering, where you really start to see very, very significant savings. Thank you guys very much.